Title of my talk is Stop Reading Changelogs, Safer Kubernetes Upgrades with Simulation. So 3 years ago on Pi Day, March 14th, 2023, Reddit suffered a 100 Pi minute long outage, a 314-minute outage. They wrote a extremely detailed postmortem, which itself, of course, was published on Reddit, and you can go read that at the link on these slides. In that postmortem, they identified that one of the primary contributing factors to this incident was a Kubernetes upgrade. They went from Kubernetes 1.23 to Kubernetes 1.24, and it turns out that in the course of that upgrade, Kubernetes changed the labels that were applied to the control plane nodes in your Kubernetes cluster. Now, the Reddit cluster that went down was running Calico. Calico required some node selectors to apply its service mesh operations, and the node selectors were pointing at the old label instead of the new one. And this caused this, again, 100 Pi minute long outage at Reddit. Now, I was not an engineer at Reddit when this happened. I'm not an engineer at Reddit now. In fact, I've never worked at Reddit, so I also know for a fact that there are a number of Reddit engineers in this room right now who were at Reddit at this time, so let's take a short detour to talk about who the heck am I and what are we doing here. So, as said, my name is David. I go by Dr. Moore in most online spaces. I have this cute little grumpy red robot, so if you see any of those anywhere, that's almost certainly me. I did my PhD in computer science. I graduated in 2014 with a focus in scheduling and optimization. From my graduate work, I went to Yelp, which was my first exposure to distributed systems. Yelp asked me to come in and apply some of my scheduling and optimization knowledge so that they could pay AWS less money on their cloud compute bills. And of particular note for this talk, while I was at Yelp, I wrote my first distributed systems simulator in order to understand some of the techniques that we wanted to apply at Yelp. I wrote a simulator for Apache Mesos to understand how these distributed systems behave. I went from Yelp to Airbnb doing the same sort of work. Then about 3 years ago, I stepped away from the bigger company life to start my own small business where we're doing research and development in distributed systems. And one of the primary projects that Applied Computing is working on is this tool called SimCube. It's open source. You can go see it on GitHub right now. And I think it's pretty cool. So with that out of the way, let's talk a little bit about why Kubernetes upgrades are hard. Over here on the right, you can see a screenshot from the Kubernetes website where they're talking about the Kubernetes release cycle. The details aren't important. The only thing I want you to note is that this release cycle is 14 weeks long. Kubernetes comes out with a new version 3 times a year. This is an extremely aggressive release cycle, and it's hard to keep up with. The internet is filled with posts like this one. Again, this is on Reddit. That says, managed Kubernetes cluster upgrades are a total nightmare. You can find dozens of examples like this. And to try to understand why, you need to understand that Kubernetes is just a sequence of n independent control loops that are all trying to operate and make the observed state of the world match the desired state of the world. None of these control loops talk to each other. Some of them are part of Kubernetes core. Some of them are totally separate, managed, written by separate people. And if you're going to do an upgrade, you need to upgrade all of these control loops in a correct but unknown order. And this is a significant challenge. Talks like the above are filled with discussions about whether you should do in-place upgrades or whether you should lift and shift and just take all your workloads from the old version and stick them on the new version. And to be honest, there's lots of trade-offs to consider there, and there's not really a right answer. But let's look now at what a typical upgrade process might look like for Kubernetes. Step 0 is someone tells you that you have to upgrade. That someone might be your boss, but more likely it's one of the cloud providers. If you're running on AWS or GCP or Azure, they typically only support the last 2 to 3, maybe 4 versions. If you're willing to pay them a bunch of extra money, they might let you stay on an older version for a little bit longer. But the cloud providers act as a forcing function to upgrade your workloads onto the latest and greatest version. So someone's told you, hey, we've got all these clusters, you've got to upgrade them. What do you do? Well, step 1 might be, well, let's go read some changelogs. We've got lots of things that we're installing in our cluster. Let's go look and see what it says in the changelogs about what might break. Over here on the right, again, this is a screenshot of the Kubernetes 134 changelog. I don't know if you can see it in the back, but right in the middle, in tiny font, it says urgent upgrade notes. And then right below that, in parentheses, it says, no, really, you must read this before you upgrade. This bullet point, by the way, is in the middle of a 2,000 line long YAML file, or Markdown file, rather. And people are expected to go and find these urgent upgrades that you really must read. Not just for Kubernetes, but if you run Carpenter or Calico or any of the other hundreds of components that you might want to install in your Kubernetes cluster. So, okay, you've done your homework. You've read the changelogs. You've identified some issues. Maybe you've fixed some things preemptively based on what you've learned. The next step is you go spin up a test environment. Sometimes we call it testing, sometimes we call it staging. It doesn't really matter. And whatever upgrade process you've chosen, whether this is lift and shift or if you're trying to do an in-place upgrade, you're going to do that process in your test environment and see what happens. You go through and maybe it doesn't work. And so then you fix an issue and then you try it again. And go through and it doesn't work. Eventually you get to the point where you're confident enough with your changes that you can do your production upgrades. And so maybe you start with your lowest risk production clusters and then you step through higher and higher risk until you get to your most critical clusters. Oops, you missed an issue. I hope you have PagerDuty turned on. This also leads to one of the other significant challenges with dealing with Kubernetes upgrades is that there is no rollback plan for doing a Kubernetes upgrade. You literally cannot go from a higher version to a lower version of Kubernetes. So your choices at this point in time are restore from backups. You do have a backup, right? You've tested it. Or you can fail forward, try to identify the problem and fix it in production while your site is hard down. And this is, if you go read the Reddit postmortem, this is exactly the choice that Reddit was faced with after their Kubernetes upgrade. So there's one point in this process which sounds really great, which is we're running this in a real test cluster. Why don't we do that more? And there's a bunch of reasons why people might not do stuff in test clusters as much as we might like. One is that provisioning a new cluster is often challenging. I've been at organizations where you can click a button and you get a new cluster in 30 minutes. I've been at organizations where it takes 3 weeks and code changes in 10 different repositories to provision a new Kubernetes cluster. And I know there are people all over the spectrum there. So even getting to the point where you can test your upgrade is often challenging and time-consuming. More to the point, test clusters are expensive. Particularly if you want to do any sort of load test or scale test or even like just mimic prod, because the most challenging and gnarly issues usually show up at scale. That's going to be like you've got to spin up 1,000 nodes in your test cluster now. And if you go to your boss and say, hey, I need $1 million so I can spin up a test cluster to make sure that production is safe, they're going to say, no, try again. And the last challenge that I want to highlight here is that, okay, you've got a test cluster. Maybe you even got permission to do like a load test or a scale test. Replicating your production environment is impossible. There's always things, even in the best staging environment possible, there's always things that are going to differ between staging and production. In production, you have real users interacting with your real cluster, doing all kinds of crazy things that just aren't going to show up in any sort of a staging environment. And so even once we've gotten to this point, it's really hard to identify and catch all of the issues that might bite you when you do one of these major infrastructure upgrades. So my question is, well, can't we do this a little bit better? I know this is challenging. There's a lot of hard problems here, but surely there's got to be something better we can do here. This is a picture, by the way, of Tower Bridge in Sacramento. I'm based out of Sacramento. It was 90 degrees last week, so I'm really happy to be here where it's not 90. But why is there a picture of a bridge? Well, if you look at most other engineering disciplines, civil engineering, you wouldn't build a bridge without simulating it first. If you look at aerospace engineering, you're not going to build an airplane or a rocket ship without simulating it first. And yet, for some reason, in our field, my experience has been that most people don't reach for simulation as one of the tools in our toolbox. I think there's a lot of reasons why, but one thing that I want to highlight is distributed systems are already hard. Simulating a distributed system is just as hard, if not harder. But in this case, I think there are a couple of things that help us out here. One thing that's going to help with our simulation process is that Kubernetes is declarative. This is a very smart and intentional design decision by the Kubernetes architects, where you just write down in a YAML file what you want the world to look like. And Kubernetes has all of these control loops that tries to match the existing observed state of the world with what you wrote down in your YAML. And I know that we kind of love to hate YAML, but for simulation purposes, this is a real benefit, because it means that at every step in your process, there's a well-defined snapshot of what we want to happen, and we can just capture and record those YAML blobs throughout your entire life cycle of your cluster. And we can record that snapshot of YAML into something that we call a trace file, and then we can replay that trace file later on in your simulation environment. And again, it's all just YAML, and Kubernetes knows how to speak YAML. So that's one thing. The other thing that is a benefit for simulation here is that Kubernetes provides an extensible API and controller pattern, which is well known if you've done any sort of Kubernetes development. I'm just kidding. This is YAML again. So what is a node in Kubernetes? A node is a blob of YAML that got written to etcd. What is a pod in Kubernetes? It's not a Docker container, it's not an application, it's a blob of YAML that got written to etcd. And so, if you write a blob of YAML to etcd that looks like a node, and you believe really, really hard that this blob of YAML is a node, then Kubernetes will start to believe that as well. And if the Kubernetes scheduler says, hey, here's a pod, I'm going to schedule it to this thing that I believe is a node, and you believe really, really hard that that pod is also real, then Kubernetes will start to believe that too. So Quack is Kubernetes without kubelet. It's a open source project that SimCube is built on top of. That's exactly what Quack does. Anytime a new node object or a new pod gets written into etcd, Quack will walk that node or that pod through its life cycle without having to have any hardware or any Docker or any code to back that up. And this is super cool because what it means is that I can run a 1,000-node Kubernetes cluster on my laptop. It's a very, very cool capability. So with that in mind, let's briefly look at how SimCube works. This is an architecture diagram for the software. I don't need you to understand it right now. What I want you to take away is that there's two pieces. Over here on the left, you've got your production cluster. We're going to install a simple, small watcher in your production cluster that just is collecting all of the changes over time. And then at any point in time, you can say, hey, give me a snapshot of your cluster between 10 o'clock and 12 o'clock, and save that into some persistent data store. Now you've got a time-stamped series of YAML changes that you can replay in your simulation environment as often as you want. So over here on my right, I've got my simulated Kubernetes cluster, which takes that trace file and it replays all of the events in there. And now here's where it gets really cool, is you can make changes to that simulated environment. So for example, for this talk, what if you upgraded the Kubernetes version in your simulation environment? And then you replayed your production data on that upgraded Kubernetes cluster. Now you can start to maybe catch some of these issues locally on your laptop before you spin up any sort of testing or staging environment. So I'm going to briefly show you how this all looks. So the first thing that I want to look at here is what is actually a trace file. Here I'm using Scuttle. This is the SimCube CLI that users can use to interact with SimCube. And if we look at a trace file, you can see it's literally just time-stamped YAML. We can go into one of these events, and we can look at it. It's just a Kubernetes manifest. That's all it is. The application that I'm running here, this is a toy social networking application. So you can do things like have a user timeline where users follow each other. You can have some microservices that handle, writing posts. You've got like a social graph. The details of that are not important. Here, what I want you to see is that over time, the configuration of these Kubernetes objects change. And that's what's getting recorded in this trace file. So let's go ahead and run this in a simulated environment. When you do Scuttle run, it tells SimCube to start a simulation. It prints out a bunch of metadata to give you some information about what you just asked it to do. And we can take a look at the pods that SimCube creates here. So here you can see we've just created a testing driver. So the SimCube driver is the thing that's responsible for downloading that trace and replaying all of the events in your simulation cluster. You can also see here that we have a whole bunch of nodes in my cluster. So this is running on my laptop. I'm using Kind. This is Kubernetes in Docker. There are two real nodes in my cluster. I've got a control plane node and a worker node. These nodes are running like Kube Controller Manager. They're running Carpenter. They're running all of my control plane components. All of the other nodes here are fake. And you can see that over in the version. These are managed by Quark. So there's no hardware there. There's nothing to support those other than YAML. And finally, we can go into the simulation namespace, and we can see that all of these pods that are fake are marked as running. And this is, again, Quark walking the pods through their life cycle. Right now, we've got 1,000 pods running. This particular simulation will scale up to like 5,000 or 6,000 pods, around 100 nodes on my cluster, but you can go much bigger than that. So I have one more thing which I think is pretty cool that I want to show off. We've actually got a cron job that's running in my simulated environment. And cron jobs are kind of unique because unlike your normal workloads, which start and then just run forever, cron jobs or any other sort of batch workloads have like a start time and a stop time. And what SimCube is able to do is it's able to, in your production environment, track the life cycle of these pods and replay that life cycle in your simulated environment. So here you can see that we've had one pod from this cron job that is succeeded, and then we had another pod that was running, and now it's marked as successful. And I think this is super cool. It gives you all kinds of possibilities and capabilities that you maybe didn't have before. I'm going to skip ahead a little bit here. So, OK. I just showed you on a Kubernetes 1.24 cluster. We ran this trace. Everything was successful. Now, 1.24 is pretty old. So let's try to do an upgrade. Let's see what happens if we replay this same trace on Kubernetes 1.25. So I'm going to do the same thing as before. We're going to run our trace. It prints out some metadata saying, hey, this is what you just asked me to do. And let's see what happens. Now, I fully acknowledge that this next piece that I'm going to show you is not the most ideal user experience. This is something that we're working on. But here, just like before, we've got our testing driver, the pod that's responsible for replaying this trace. It was running. Oops, it failed. OK, well, that's interesting. So let's go ahead and look at the logs to try to understand why it failed. Again, not an ideal developer experience. We get a traceback. Let's scroll back here a little bit and see what happens. Up at the very top, we get an error message that says the requested resource could not be found on the server, and we get a 404 page. I know this is a pre-recorded video, but I left this in here just to prove that it's real. This is me fumbling around in the logs a little bit to try to find the next right line to show you. It's the real SRE experience right here. OK, so here we go. Here are two log lines, one that tried to create our user database cleanup cron job, and then the log line that follows immediately after that is the same message that we had before. The requested resource could not be found. Now, if you know anything about Kubernetes history, you probably know the punchline already. In Kubernetes 1.24, we used the v1 beta 1 version of the cron job API. So Kubernetes uses versioned APIs, which allows them to make changes iteratively without necessarily impacting what customers are doing in the past. In 1.25, the v1 beta 1 API was removed from Kubernetes, which means that if you try to create a v1.beta1 cron job resource in Kubernetes 1.25, it's going to fail in exactly the way that we just saw here. So OK, we've identified a problem. Let's see how we can test our fix in simulation. So SimCube includes a built-in bespoke DSL that allows you to make targeted changes to your trace files so that you can experiment and try things out. This is Skell. This is the SimCube expression language. Here I'm going to show you a really basic Skell file. So what this is showing is it has a single command in it. I'm going to say take everything in my trace that has kind equal to cron job, and I want to change the API version of that object from batch/v1 beta1 to batch/v1. We can apply this transformation to our old trace file that didn't work. to produce a new trace file that has all the same events, but has an upgraded cron job API. So let's see what happens here. So we run scuttle transform, we take our old trace file, the scell file that I just showed you, we output a new trace file. We see that it matched one event in the trace file. It modified one event. This is the user DB cron job that we saw. And now we've got a new thing we can look at. In fact, we can open that up and just confirm that it made the changes that we wanted to. We're going to scroll down for a little bit. Here's our cron job. And you can actually see that the API version now is listed as batch/v1 instead of batch/v1 beta1. And we can now try again. We can take this trace file, we can replay it in our 1.25 Kubernetes simulation environment, and we can see if there are any issues that come up. And so here, just like before, the driver pod will come up shortly. There it is. And if we sit here and watch it, last time it crashed around the 10, 11 second mark. Here, if you watch, it will just keep running, which is great. Seems like things are successful. We can actually go into the namespace where all of our simulated pods are being created. We can see that those pods are getting created like they're supposed to. We know there's an issue with this user database pod, so we can take a look at that. We see that we've created one of these cron pods, and just like before, Quack and SimCube are walking this pod through its life cycle where it eventually succeeds. So cool, we've just used simulation to diagnose an issue with a Kubernetes upgrade and identify and validate a proposed fix. But we're all SREs, so we like to automate things. This was a very manual process that I just showed you. What if we could automate this entire pipeline? And what would that look like? In your organization, you collect traces from your production clusters. Maybe you collect one once every quarter. Maybe you collect one once a week. I don't know. You have a few representative trace files that you plug into a well-known location, and then you stick a simulation into your CI pipeline that downloads those trace files on, you can do some periodic basis or whenever you have to do a Kubernetes upgrade. And this gives you some degree of confidence that things are going to work for you. It also gives you like a baseline. You can track the results of these simulations over time because it's all automated and you don't have to have someone manually doing all of this. Over here on the right, this is a screenshot of the SimCube GitHub repo where we've done exactly that. We have an end-to-end test that runs simulations on every merge to main in SimCube. And this is just to make sure that SimCube itself is behaving the way that we expect. This is something that you can do too. We have right now on the AWS Marketplace a free AMI that comes with all of the SimCube stuff installed that you can just go look at. We're also, if there are any Amazon engineers here, I need a final approval on the GitHub Action AMI that we're publishing. So if you could help me out, but hopefully that'll be in the next week or so. We'll also have a GitHub Action AMI. So if you want to plug this into your own repos to start running simulations and to start playing around with that, that's a capability that you can absolutely do. So let's wrap up. How can SimCube or simulation in general help with upgrades? Well, we'd identified a few pain points at the beginning of this presentation. With simulation, it's easy to provision your simulation environment. I can do this in less than a minute on my laptop and get a 1,000-node cluster going. It's also, well, okay, freeze may be an overstatement, but this is like pennies. You still need a physical laptop or like an EC2 node or something to run your simulation, but that's way less expensive than trying to provision a 1,000-node cluster to do your scale test. And replicating your production environment's impossible. So one thing I want you to take away from this talk is that I'm really excited about all of the capabilities that I just talked about, but it's not a silver bullet. Simulation, by definition, is throwing away data so that you can represent something that's otherwise hard to reason about. And your hope is that you've thrown away the right data so that you can still gain insights about your production systems. So I'm going to highlight just a couple areas here where SimCube may not help you. There's no application code running. So anything that's making requests to your applications over a network is just not going to work because there's nothing there to respond to it. There are different tools that do this type of application load testing, and I would encourage you to use those tools. Anything that relies on metrics isn't supported yet. So I lied a little bit earlier in the presentation where I said that everything in Kubernetes is YAML. Only like 98% of things in Kubernetes is YAML. But you do have some things like your horizontal pod autoscaler or some other types of controllers that rely on metrics from your CPU utilization or memory utilization. This stuff isn't supported in SimCube yet, but technically, you can just generate a fake metric stream and pipe that into your simulation environment and then start to get results for your HPA or any other types of controllers that rely on these metrics. So this is something that I'm really hoping that we're able to make some progress on in the next 6 months or so. The last thing that I'll highlight here, I said cloud providers, no shade at the cloud providers. Any sort of third-party service that interacts with or runs on top of or that Kubernetes depends on starts to get tricky. The cloud providers, if you're running on EKS, for example, you don't get to see the control plane. You don't know what's happening behind the scenes there. There are still things that you can do to simulate in these types of environments. But it's harder. And so what I'm really hoping that you can take away from this talk is, again, simulation is a tool. It's not the end all. It's not going to solve all your problems. So let's revisit the Reddit outage. And I want to ask a question. Would simulation, or SimCube, had it existed at the time, would it have prevented the Reddit outage? Well, on the one hand, maybe. Reddit people, engineers, certainly could have loaded their production data into a simulation environment. They could have upgraded their cluster in the simulation environment. They could have seen that, oh, this node label on the control plane changed from version 1 to another, and that causes Calico to behave weird. On the other hand, no, simulation wouldn't have solved this problem. As they identified in their postmortem, and as I'm sure everyone in this room knows, technical issues are just part of what go into these sorts of incidents. So in their postmortem, they identify a host of other systemic and cultural issues that contributed to this incident as well. What I want you all to take away from this is you still have to know and understand your systems. Simulation is a great tool for being able to do that, but you still have to have someone who's able to look at the results of the simulation and say, yes, this is good, or no, it's not. Nevertheless, I think this is really cool. I love getting to work on it. I think it's super exciting. If you want to know more, I have a few links up here. So there's 3 QR codes. First one links to the SimCube docs, which you can read through and find some more information. The middle one links to my blog, where I talk endlessly about these sorts of things. And lastly, I love getting to chat with people. So if you ever want to reach out and we can set up a Zoom call or meet up in person, depending on where you are, you can always reach out, and I would love to chat with you more. So that's everything I have to talk about. Thank you so much for your time. I'm happy to take questions if we have time for them.